Hey, good morning, everyone. How are y'all doing?
Doing well. How about you?
Doing okay. Doing okay.
Yeah. Got everything settled in?
Yeah. A little sleep deprived, but other than that, I'm doing okay. But thank you all for understanding. Again, hoping to be back in class on Wednesday. Just gonna figure out some logistics, but we should be. Let's just kind of keep your eyes open on your email. But the plan right now is to go back on Wednesday. So, okay, let's get started. So I wanted to take not a whole lot of time, but just some time to talk to you about the exam, just to give you an idea of what, why I took off certain points for, things that were missing, things that I expected. So on the first problem, a lot of people missed that when you look at these two curves, that there's actually two regions that are enclosed by both of these curves. Most students got one region between -2 and 2, but there's actually another region between 2 and 5. And so the only way to really see that, because if you try and just graph this on like Desmos or something, you won't see the two regions. You have to find the intersections of the curves. And when you do that, you get 3 solutions. And that's what tells you that there's going to be 2 regions. So just FYI, that's why if you got points docked off on that, that's, I said on there, 2 regions, that's what was going on there. And then you were supposed to solve that by hand and get an answer. Now, the second problem, let's see, again, I wanted to see graphs. I wanted to see your graphs labeled so that I could tell, it's a take-home exam. So my expectations were high. Also finding the intersections, I did it by hand, but it was okay if you just use the computer for that. And then the actual integration on this one was integration by parts twice. Well, each one of them required integration by parts. And then, yeah, it got a little messy, but you should have got an answer, a decimal answer there, 0.05117. And then on this one, I really wanted to see a picture again with labeling, and then using the method here of shells, because your axis of rotation was parallel to your rectangle. So, these functions in this problem were given to you. They're functions of y. They're solved for x already. So it makes sense to leave everything the way it is and then rotate that rectangle around that horizontal line. So you use shells, and here's your formula that you'd have for it. And then on this one, I said use anything you want to find the antiderivative or find the area, or sorry, the volume here. So I used Mathematica and got an answer 11.4. And then this is the same problem, just rotated around a different axis of rotation. So this time your axis of rotation is vertical, so your rectangle is perpendicular, so you want to use washers, which changes your formula. And then again, here's the setup for it, and then the Mathematica using that to get the answer. All right, this one caused some issues. Here's the graph. It's an infinite region. It goes forever, and you want to rotate around the x-axis. And I wanted it to be solved by hand, right? So you set up the integral. You're going to have a limit. It's going to go to infinity, which you're supposed to convert it to a limit. I didn't, because it was just so I could get the answers here. But in the antiderivative, you had to do integration by parts twice. And then the part I took off for is there was a step in here where you had to figure out what was happening when you plug infinity into the expression, or take the limit. And that limit you get is infinity over infinity. And you have to show that that goes to 0. You can't just say, oh, it goes to 0. A lot of people just put, oh, that goes to 0, but no work. So you have to show that. And I did it by doing L'Hopital's rule. I actually have to do L'Hopital's rule one more time. I didn't do it again because this is just for my own answers. But I'd have to do L'Hopital one more time and show it goes to 0. And then you can say it converges to pi/4. So if you were missing this, I took points off. Let's see, the next part was just to say it's finite. And then that last one was finding the area. So it's a different integral. And you set it up and hold on a second. Did I forget something there? Hold on. What was the problem? What about the area? Oh, it was the area under the curve, not the surface area. Sorry. Area under the curve. So just use a computer to do that. Some people did this by hand. That's fine. It's easier than the first problem, but you could have used a computer. This one wanted to find the arc length. So a damped oscillator, I had different answers. Most people understood. A dampened oscillator is just something that, you know, oscillates, but as you go out, it gets, the amplitude starts to shrink. And so it's dampened. And so for this one, what I wanted to see is really that you got the function, you took its derivative, you squared it, plug that into the integral, and then just use just the formula for this, and then use a computer to integrate this, and you get about 3.07 for that arc length. And then on the last one here, this was the perpendicular cross-section problem. Again, show me the region, and then try and draw me a little slice of it, come up with a formula. Most people got this set up right. It was what they did with this. That was the issue. I saw people do different things. Trig sub is one way to go about it. And if you do trig sub, you have to come up with a reference triangle and go through all that. And you eventually get to an answer 64/15 or about 4.27. Another way you could do this that some students did is they made a u substitution. U is 4 minus x squared. And then replace that with u. And then here they broke it up as x times x squared and solve that for x squared, and got x squared is 4 minus u. And then it still works out that way. I think it might actually be a little easier that way, but there were different ways to go about this, but you had to do it by hand. Okay. So any questions on that? Like if you have any questions about, hey, you took up a lot of points here and you want to clarify, just get with me and we can talk about it. But yeah, we move on. So I asked you to do some videos. How did that go? Did that make sense, what I covered?
Yeah.
Yeah. Okay. As far as where we are right now, okay, you remember what we're trying to do right now is figure out whether or not a series converges or diverges. And we have this reference sheet that we've been looking at. And if you take in what I asked you to watch for last week, we are almost done with this sheet. We've got now this idea of a P series, okay, and then also the integral test, which is kind of tedious, but pretty awesome. How do y'all feel about this comparison test? That comparison test always, like when I first learned it, that thing was weird. Like to me, I found it very strange that I had to come up with something like out of the air, like pull it out of the air to compare it to. And it's kind of a weird test, right? Like the integral test, you don't have to pull anything out of the air because the actual series itself, the formula for the a sub n or whatever, that tells you kind of what your integral is going to be. But here for comparison, you've got to come up with that b sub n. So that can be tricky. And do y'all understand that there are kind of like 3 different cases here? Like this last one is where you do the limit instead of doing a direct comparison. But do y'all understand how these work? Was that pretty clear that you have, if you're comparing to something that converges, you have to show this inequality. If you're comparing it to something that diverges, you have to show this inequality. Or you can scrap both of these and just go to the limit part where you try and show that it equals a constant. How do you feel? There?
Figuring out if it's less or more isn't so bad. It's just coming up with the comparison
Yeah, the
test.
thing to compare it, right? Yeah. So all the tests that we've used up to that point, right? All of these pretty much required that the thing that was inside was positive. And so we also talked about, or I went over last time, the alternating series test. Now, again, going back and thinking about when I was learning this stuff, to me, the alternating series test was one of the easiest tests out there because you kind of knew when you could use it. If you have an alternating series, well, you want to do the alternating series test, right? And what you need in order to show convergence is very, very straightforward. You just have to show that the sequence, this positive part of the sequence, you have to show it's decreasing. And then you also have to show that it's the limit goes to 0, and that's it. If you can show that, you're in business. So that's where we are. We still have the ratio test, the root test, and then this last little piece. That's all what I'm going to cover right now. And after we're done with that, we've got everything we need to proceed into the next sections. So without further ado, let's pick up and get going with this. So let's see here and bring up my notes. I just put these notes, I put the notes for 8.5. I put the notes for 8.5 in that folder last night, I believe. And I've kind of reorganized things. These are the notes for 8.4 that you should already have. I asked you to go all the way up. In the video, you went all the way through the examples for alternating series tests, right? Hold on. You went through, yeah, you went through all of this. And then I told you to look at, if you wanted to, the alternating series estimation theorem. So I don't know if you did. I'm going to skip it because really all the alternating series estimation theorem does for us is it gives us a way to approximate the actual sum of an alternating series. That was very useful before computers. You know, because before computers, we really didn't have a way of getting an accurate sum or going and getting it really close. So now that we have computers, we really can just type the series into a computer and say, hey, take that series out 1,000,000 terms and it'll spit out an answer. So we're not real concerned with this theorem anymore. So I'm going to just kind of like, if you watched it, hopefully you understand it. No big deal if you're confused on it. We're going to pick up or actually continue now with the next idea, which is absolute convergence. So y'all ready? Here we go. Absolute convergence. So this, again, as a student, I remember this confused me, but it's not hard once you understand it, okay? So this is a definition, okay? It's a definition. And what it's saying is that if we start with any series, okay, so that's any series at all. You can have positive and negative, we can alternate, doesn't matter what it is, okay? Any series. We consider a new series. And all that new series is instead of doing a sub n, we look at the absolute value of each of the little pieces. And then we add those up. And that means that we're never going to have any negatives in there. Everything's going to be positive. We're adding together. Okay, that's all it is. All right, so we start with a series and then we create this new series. Now, the definition here is that we will say, okay, we will say that the original series, that's our original one, right? The original one. We will say that it is absolutely convergent if, okay, I covered the word if here, if that new series converges. So start with the series, right? It could have pluses and minuses in it, whatever. Take the absolute value of each of the pieces, add those up. If that converges, then we say the original series is absolutely convergent. All right, that's it. That's the definition. So I'll explain why this confused me as a student in a minute as we go through some examples here. So the first example here that we're going to look at, I'm going to go to a different page. I worked it out already in the notes, but I'm going to work it out here. So let's take a look at this series. So when you look at that, is everyone just, you know, if we take a step back, is everyone clear that this is an alternating series? Right? It's an alternating series. How could we check to see if it converges or diverges? If I asked you, hey, does that converge or diverge? What would you use? What test would you use?
AST.
The AST, alternating series test, right? So you could use the alternating series test here and go after this, and you could figure out if it converges or diverges. And it actually would be very easy to show that that converges, all right? That's not what we're doing here though, okay? What I want you to do is I want you to consider the sum n equals 1 to infinity of the absolute value of this series, all right? Now, when you do that, do y'all see that the -1 to the n will no longer matter? Because if we take the absolute value of it, you'll always get a 1 on top, right? Because you're gonna take the absolute value. If it's 1, it's 1. If it's -1, you take the absolute value, it's 1. So this really turns into this series. And I don't need the absolute value on the n squared either, because n is always a positive number, right? Because we're starting with n being 1. So no matter what, n squared is positive, so I don't need an absolute value. It's not going to change anything. So do y'all agree that the sum of the absolute value of the pieces in here, this is just really 1 over n squared, right? What type of series is this? So you have to recognize this.
Is it harmonic?
P series.
So it would be harmonic if that was a 1. It's a P series though. So remember on your test, this again was from last time. We have this P series. If you have summation n equals 1 to infinity of 1 over n to the P, this is a P series. And here for us, P is 2, right? And if P is greater than 1, it converges. So I know right now that this right here is a P series with P being 2, which is greater than 1, which means we have convergence, right? So who cares, right? Who cares? Well, all we can say now is this, therefore, okay, therefore, the original series I'm not going to conclude right now that the original series converges, okay? What I'm going to say is that the original series is absolutely convergent. Absolute convergence means it's not, again, it's not saying that the original series converges, although it is going to turn out to be that. By doing this, what we're saying is that the original series is absolutely convergent. That's it. It's absolutely convergent. That's what we call it, because the sum of the absolute value of the pieces converges. All right, that's it. Again, we could have run the alternating series test. We didn't do it. If we did this, we would converge. Okay, I'm not going to show the work, but we would converge. All right. All right, so let's try a different example. All right, because that one was a little straightforward, a little too straightforward. Let's see. Yeah, okay, so with the next example, let's look at this.
Real quick, I just wanted to ask you, I think I missed the point of why we did that, because I mean, what's the whole point of making it absolutely convergent? Is it because we saw the P series? Is that what made it?
Wait, what's the point of making it absolute?
Yeah, because like I think I missed that point. Like, so we just did the absolutely convergence thing. Is it because so we could see that P series? Is that the reason why we did it?
Why we did the absolute value?
Yeah.
Okay, the only reason we did the absolute value is because I was trying to establish a definition. So this definition of absolute convergence means that when you look at a series and take the sum of the absolute values, you look to see if that converges. If it does, then we can call it absolutely convergent. All right. We're going to have a theorem in just a minute that says if you have absolute convergence, okay, if you do, then the original series guaranteed converges. All right.
Yeah.
So the first thing we have to establish is, what does absolute convergence mean? It means you take the sum of the absolute values and you see if it converges.
Okay.
Look at this example. Look at this example right here. That is also an alternating series, right? So if I asked you, does that converge or diverge? You could simply do the alternating series test and you could show that that does converge, okay? Do I need to run through that, or are y'all okay with that? Would y'all like to see the alternating series used on that or test?
Can we see it? I would
Yeah,
appreciate
we
it.
can do it. So if I run the alternating series test on this, what I need to do is I need to rewrite this sum. I need to split off the part that alternates -1 to the n. I need to split that off from the other part, which would be just a 1 over n. So the first step for alternating series test is to isolate the part that's positive away from the thing that's switching the signs. Once you have that, I believe in the notes, I called that B sub n. What you need to do now are two things. First thing you need to do is show that B sub n decreases. And then the second thing you need to show is that the limit as n goes to infinity of B sub n equals 0. Those are the two things you have to show. All right, so to show decreasing, what that means is that B sub n plus 1, or sorry, B sub n is bigger than B sub n plus 1. So all I do here is I plug n into that piece, right? That's just going to be 1 over n. I have to show that that's bigger than 1 over n plus 1. And then if I just cross multiply, I get n plus 1 is greater than n. And if I subtract n from both sides, I get 1 is greater than 0, and that's true. So I've shown the first thing I need to show for decreasing sequence. Or sorry, I've shown the first thing I need to show for the alternating series test, right? Now, the next thing I need to show is that the limit of that B sub n goes to 0, but that's super easy because limit n goes to infinity of 1 over n is 0. And that's obvious because it's fixed over infinity, and that's 0. So right there, I'm done. I can say, therefore, the original series converges. Okay, that's if I were to just give you that series and ask you, does it converge or diverge? That's what you would do. Now, different question. Is this absolutely convergent? That's a different question. So what you need to do now is take the sum n equals 1 to infinity of the absolute value of that sequence in there. And when we do that, you no longer need the absolute value. You can get rid of the -1 to the n on top. You just get 1 over n. And that is harmonic. That is a P series with P being 1, right? A P series with P being 1 is harmonic. So what do harmonic series do?
Diverge.
Diverge. So what can we say then? Therefore, be real careful here. What we can say is this: the original series what can I say?
Does
Can I
not
say-
absolutely converge.
Is what?
Does not absolutely converge.
Does not absolutely converge. Well, I'll say it this way: is not absolutely convergent. Now, be so careful with this, because the absolute value, right? This thing, it diverged, right? It diverged. That does not mean the original series diverges. That's not what it means. It just means that the original series is not absolutely convergent. Does the original series converge? Well, yes, right? The original series converged. We showed it over here. But the absolute value of this, right? The sum of the absolute value of this thing doesn't converge, it diverges. And so even though this series is convergent, it is not absolutely convergent. Understand? It is convergent, but not absolutely convergent. Absolute convergence is a very, very strong condition. Go back to the one we did before this. I did not show this with the alternating series test, but on this problem here, it converges, but it's also absolutely convergent. That's a very, very strong condition, because that means the original series converges and the absolute value converges. That means it's absolutely convergent, right? And convergent at the same time. But you don't have to, you can have convergence, but not absolute convergence. You can have that happen. Okay, let's continue. Close this out. Okay, so now this example that we just did, right? This hopefully y'all can see that. Let's go a little bigger here. The one that we just did, okay, that problem, we just did that one, okay? Hold on, sorry, that's not the one we just did. Here we go. This is what I meant to hit. Sorry, I hit the wrong button here. Okay, so in the problem that we just did, right, this is the one we just did, -1 to the n over n, right? The alternating series test shows us it converges, right? This converges, but the absolute value doesn't. It diverges. When that happens, we will say that the original series is conditionally convergent. All right. So if the original series converges, but the absolute value diverges, that's conditional convergence. Got it? So now we get to a theorem. All right, and this theorem is pretty simple. It says if a series, give me any series, if it's absolutely convergent, which means that if you take the absolute value and it converges, then it itself is convergent. Now, there's a much cleaner way to look at this. Go to your series test and go to the very last one, the very last test. This is the test. It says, look, if you take a series and you take the sum of the absolute values and that converges, if it does, then the original series converges. The way to think about this is, let's say you have a series, right? The way I like to kind of consider this and understand it is, let's say you're trying to figure out what a series does, right? Let's say you have some series A sub n. And let's say that, it adds up some numbers. Yeah, maybe you have a positive number and you're adding it to another positive number. And then maybe you add a negative number, and then maybe the next one's negative, and maybe the next one after that's negative, and then it's positive, and then maybe it's positive. And you're adding all these up, right? And you're trying to figure out what the hell is that, right? And it goes on forever. This theorem says, well, look, if you take the absolute value of all those, right, then it turns them all into positives, right? Now you have a bunch of positive numbers. Forever. It says, look, well, if this converges, right? Let's say that goes to a number, right? If this goes to a number, then if you go back and look at the original one, all you're doing here is you're taking away from that, right? You're taking some, it's going to be smaller than this thing. And so it can't be infinite because you're taking things away from something that's already going to a number. So you're guaranteed the convergence. Now they don't converge to the same number, but it converges. That's the theorem. Does that kind of make sense? You add up a bunch of positive things to get a number, then taking a few negative things out of it is still going to be convergent. That's the theorem. All right. Let's see. This is a good example. Yeah. So look at this one. Let sum n equals 1 to infinity of sine of n over n squared be our series. I want to know right now. Okay, my question to you is this. I didn't put the question here. Does this converge or diverge? Does it converge or diverge? So let's look at this series. First of all, please recognize that this is not our traditional alternating series. An alternating series must be plus, minus, plus, minus, plus, minus, or minus, plus, minus, plus, minus, plus. So we need that -1 to the end to make the alternating occur. That's what an alternating series is. This is not an alternating series, so I cannot use the alternating series test. Understand? And to kind of help you see that, if you just take the sequence here, not forget the sum. If you just take the sequence here, if we were to plot this sequence, I plotted it here for you. You can see that, you know, your first term here, your first term in there, if you plug in n is 1, you get a positive, 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 and then you start getting negative, negative, negative. Then it looks like it goes positive, 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 and then it looks like it's going down here, negative, 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 then positive. It looks like 3 positives again. Anyway, the whole point is it's not positive, negative, positive, negative, positive. It's not a true alternating series. So because of that, we cannot use AST, right? So cannot use AST. It's not alternating. But what I can do is try this new idea of absolute convergence. So let me take this and let's take a look at the sum as n equals 1 to infinity of the absolute value of sine of n over n squared. So I did not do the absolute value on the bottom. Okay, the reason I didn't do the absolute value on the bottom is because n squared is going to be positive no matter what. Y'all good? Y'all understand what I'm doing? I'm trying to check right now. The question here is this absolutely convergent? Right? That's my question. I'm trying to figure out, is this thing absolutely convergent? Because if it is, what can I say? If this thing converges, then the theorem says, oh, well, then that converges, right? If the green one converges, the blue one converges. So now we have to figure out, how do you show that the green one converges? Right? How do you do it? Any ideas? What does that kind of look like to you?
Oh, comparison
series,
test.
maybe?
Yeah, why don't we compare it to something? What do you want to compare it to?
1 over n squared.
1 over n squared. Let's try it, right? We can try to compare that to 1 over n squared. Now, remember what the conditions are for the comparison test. Very important. The conditions for the comparison test, and I can't stress this enough, is that if you're going to do a comparison test, the series that we're looking at, the pieces of the series have to be positive for us to do a comparison test. They have to be positive. And that's why it's really important that we do this absolute value, because you cannot do a comparison test on the blue one, because it's got negative stuff in there sometimes, doesn't it? Like for some values, your sign's going to be negative. So we cannot do a comparison test on this. But if you take the absolute value, then you can, because now everything's positive. Understand? So we're going to compare it. So we're now going to do a comparison test. And I think, Ian, you said you want to compare it to 1 over n squared?
Yeah.
Okay, I like that idea. What do we know? We have to know something about this, right? We have to know what it does. And we do, right? Because what type of series is this?
P series.
P, right? P is 2, which is greater than 1. This is convergent, right? That's a convergent series. Now, so we're looking at our series that's in green, and we're comparing it to a series that's in gray, the gray series here, and we're comparing them, and the gray series converges. So now we have 2 roads we can go down now, all right? We have, when you go back to your series test, God, mark this up too much here. What we have now is this. We're looking at a comparison test. We have 2 choices. Because the series we're comparing it to, because it converges, we can just try and show that this inequality is true, okay? We have to throw this out because the original series, the series we're comparing it to does not diverge, so we're not doing that. So we can either do what's in green there, or if we want, instead of doing this inequality, we can do this limit. And I showed you all that sometimes one works and the other doesn't. Sometimes they both work. So what would y'all prefer? Would y'all prefer I do the inequality or the limit, or do y'all want to see it both ways? I don't care.
Both ways.
Both? Okay, so I'll do it both. So I'm going to split this up into two different ways, okay? So the first way I'm going to do it is I'm going to say that I want to show, what do I want to show? If this one converges, I need to show that, according to the test, that the A sub n is less than the B sub n. And A sub n is the original series and B sub n is the new series. So for us here, this is A sub n and this is B sub n. So since this converges, I want to show that all of these are smaller than those. So I want to show that the absolute value of sine of n over n squared is less than 1 over n squared. That's what I want to show, right? If I can show that that's true, I'm done. So just multiply both sides by n squared. If you multiply both sides by n squared, you get absolute value of sine of n is less than 1. Less than 1. Hold on, it can be equal, sorry. It can be equal. Look at the inequality here. Sorry, it can be equal. See that? Less than or equal? Add that. Yeah, because that now it's true, right? This is always true. The sine function is bounded between -1 and 1. And so if you take the absolute value, you're always going to get numbers that are between 0 and 1. So isn't this true? So since that's true, right? So therefore, what can we say? We can say that the absolute value of sine of n over n squared converges, right? That's what the comparison test just told me. I compared the green one to the gray one. This inequality held true, which means that this green one converges. But what then does that tell us about the blue one?
That it absolutely converges.
That's right, that this one, without the absolute value on top, converges absolutely. And therefore, by the theorem, specifically theorem in our notes, theorem 8.4.12, this series converges. So I hope that you can see in this example how, this is what makes the testing of this so hard, because you have to show your train of thought. You can't just give me like, yes, it converges, no, it diverges. You can't just give me a correct answer without any work to support it. You have to justify it. So just to recap, we started with the blue series, couldn't use alternating series test because you had negative pieces in here that were kind of oscillating around. So we took the absolute value and said, hey, what does this do? Oh, let's compare it to this 1 over n squared. Okay, we'll use a comparison test. We'll show this inequality is true. Once we said it was true, that told us that the green one converged. Once we knew the green one converged, that meant the blue one converged absolutely. Once we know that the blue one converges absolutely, then the theorem tells us it must converge. There's a lot going on there. Now, the other option would have been, instead of doing the inequality, we would just do the limit as n goes to infinity. So I'm going back to this test here. I would be doing this part instead. Take the limit of the a as n goes to infinity of the a sub n over b sub n. So that would be the absolute value of sine of n over n squared. Take that and divide it by 1 over n squared and see what happens. And what do you get when you flip and cancel? What do you get here? Limit n goes to infinity of what? Just absolute value sign of n, right? Does that converge?
No, it doesn't work because it's like jumping up and down.
That's right. That thing is that I showed a graph of this a long time ago. It looked like a bunch of dots everywhere, right? They're just kind of up and down everywhere. It's not going to a number, right? So if you look at your series test, what we need is for this limit to actually go to a number, right? We need this thing to go to an actual number, some positive real number. And it's not, right? It's not doing that. So Adair or Cruz, I forget who asked me to show you both ways, right? If you had done this way first, this limit right here doesn't exist, this would have failed, okay? Now, that does not mean it diverges, okay? That doesn't mean it diverges. It just means that that test failed. So you would either say, oh, I need to compare it to something else, or you say, let me try the inequality. The inequality actually works. So when you look at this series test for comparison, I really try and make sure my students understand, like I personally always love to go after this first. Like I always like to, let me try the limit, okay? Because the limit a lot of times will get you there, but sometimes it doesn't. So if it doesn't, don't give up, then move on to the inequalities, depending on what you're trying to show. It could be either, convergence or divergence, depends, but try the limit first. If you get a positive number, you're good. If not, you move to the inequality. If that doesn't work, well, maybe you're comparing it to the wrong thing. Maybe you need to compare it to something else. Or maybe the comparison test isn't the way to go. Maybe you should use a different test. Okay. We having fun yet? We are now 8.4.14. The almighty ratio test. All right. The book doesn't call it almighty. I call it almighty. This is the one. This is the big daddy right here. All right. This is the test we are going to pretty much use the rest of the way. This test is super powerful. It works almost all the time. But again, don't marry yourself to it, okay? Because there are times where it fails. But it's so useful, all right, this test. So what is the ratio test? I'm going to say this test is the most important, all right, and useful. The great thing about it is that it can be used on any series. Like you don't have to have alternating, you could, if it's alternating, you can use this test. If it's just positives, you can use this test. If it's like the problem we just did, you can use this test, all right? And here's the way the test works. What you're going to do is you're going to, start with your series, whatever it is, right? Okay, and you're going to take a look at that a sub n in there, and you're going to take a limit. You're just going to take a limit of this, the absolute value of a sub n plus 1 over a sub n. So what you're doing is you're taking the limit of the ratio of the n plus 1 term divided by the nth term. So if you think about what a series is, you're adding up 1 plus 2 plus a sub 1, a sub 2, a sub 3, you keep on going out. What you're doing is you're going out there and you're taking the nth one and the one right next to it. And you're taking these two and you're creating a fraction out of them, and you're letting n go to infinity, and you're trying to see whether or not that ratio is less than 1 or bigger than 1. And the way to think about it is, I don't know if this makes sense, but let's say I take these two numbers and I divide the a sub n plus 1 by a sub n. If that ratio is bigger than 1, what it means is that the next term going out is like trying to get further and further away from you. And so it diverges. Now, if the ratio is less than 1, then that means as you go out, the numbers are starting to get closer together. And so it should converge. Now, the trouble comes when the ratio is exactly 1. When the ratio is exactly 1, this test fails. All right. So that's it. You just have to be able to run this test. And if it comes out to be less than one, you've got convergence. If it comes out to be greater than one, then you have divergence. And if it's equal one, then you're crying in the corner because it's no good. All right. Beautiful test. We're not going to prove the test. We're just going to use it. So here we go. Let's do some examples. Here we go. So the first one that I'm going to do is this one. All right, so let's talk about this before we get right into the ratio test here. We could use the alternating series test, right? Because it is an alternating series. Other than that, we really don't have any way of handling negatives other than the alternating series test, or we could check to see if it converges absolutely. So we take the absolute value, which would get rid of the -1 to the n, and we can maybe see what that does and compare it to something, maybe. But screw that. Let's try the almighty ratio test. So here it comes, ratio test. So I'm going to run this limit. The limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, which equals the limit as n goes to infinity, the absolute value. Okay, a sub n plus 1 means you plug n plus 1 into this formula, right? That's a sub n right there. So let's plug in n plus 1. We should get -1 to the n plus 1 times n plus 1 to the 4th power over 4 to the n plus 1. But then I need to take all of that and divide it by -1 to the n times n to the 4th over 4 to the n. I need the absolute value of all of that. And I just need to know what happens when n goes to infinity there, which might initially look like a nightmare, right? That does look pretty complicated, but there's going to be so many nice things that happen here. First, I'm going to completely ignore the -1 to the n's, because when I take an absolute value of those, they're going to go to ones, right? So I don't even care about those. And then the other thing I'm going to do is, since I have a fraction over a fraction, I'm going to take the first fraction up here, which is n plus 1 to the 4th over 4 to the n plus 1. I'm going to multiply it by the reciprocal of the bottom, which is 4 to the n on top and n to the 4th on the bottom. Right now, if you let n go to infinity, you're going to get infinity over infinity times infinity over infinity. You've got a lot of infinities going on here. So you might be thinking, oh, I'm going to bring in L'Hopital. Not yet. There's a lot of algebra we can do still. So one thing I'm going to do here is I'm going to rewrite the denominator of the first fraction as 4 to the n times 4. And then this is 4 to the n and then over n to the 4th, like that. So all I did was rewrote 4 to the n plus 1 as 4 to the n times 4. Is that all right with everyone? I think we've done that enough with like geometric series and stuff to understand that. Cancel the 4 to the n's. And then look at this. I have really, if I wanted to, I can look at it this way. I have an n plus 1 to the 4th over a 4n to the 4th, like that. Right? That's what I have. Now you could do L'Hopital here and start taking derivatives, but I'm going to go even further. Watch this with algebra. I'm just going to write this as 1/4 times n plus 1 over n to the 4th. So I just took that 4 that was out on the bottom here out front. I just brought it out as a 1/4. And since both of those, the n plus 1 and the n were both raised to the 4th power, I just rewrote as n plus 1 over n to the 4th. And then now what I can do is I can just mentally think about this. What happens as n goes to infinity right there? Inside, you get infinity over infinity, right, in the green, and just hit that with L'Hopital one time and you get 1 over 1, right? So this thing goes to 1, and then 1 to the 4th, that goes to 1. So your answer should be 1/4. Understand? So what's our conclusion?
Converges.
It converges because this answer is less than 1. And the ratio test says that if you run this limit, and get an answer L that's less than 1, then you've got convergence of the series. What do y'all think? Pretty good, huh? Where's the next one? All right, why don't you try this one? Get it set up. See if you can get at least the limit set up. Limit n goes to infinity. Absolute value a sub n plus 1 for a sub n. Let me give you a few minutes, see if you can see how far you can take this one. I'm going to start working this and just work it silently here. And you can look and see how you're doing with it. Okay, I'm at a crucial step here. Does anyone have any questions on what I've done here? Replace all the n's with n plus 1s. What are some of the common mistakes I see? I'll see people rewrite this when they plug in n plus 1, they'll put n factorial plus 1. That's not what we're doing. We're also not doing this. You have to write it in parentheses, okay? So n plus 1 in parentheses factorial, n plus 1 to the n plus 1. I canceled out the negatives, negative 1s, and then I multiplied by the reciprocal. What am I going to do next? What do y'all think? what can I do with this? N plus 1 factorial. There was a property of factorials that I asked you all to remember. Let me see here. This is actually in the sequences section when we were talking about factorial 8.1.7. If you go to 8.1.8, a special property of factorial, right, is that when you have n plus 1 factorial, that can be rewritten by peeling off 1 of the factorial. So I can rewrite this as n plus 1 times n factorial. That's really an important property. We need that now. And then when we do that, this n factorial will cancel. So here's where we are. We have limit, and it goes to infinity. We have absolute value. We have n plus 1 to the n plus 1 over n plus 1, and then n to the n. Anyone see something else I can do? Can I do this on top? I can do that, right? And n plus 1 to the n plus 1 is the same as n plus 1 to the n times n plus 1. And so then I can cancel out the n plus 1s. And then both of those, both of these are raised to the n, aren't they? This is the same as n plus 1 over n all to the n. Now what?
Wait, sorry. I was a little bit confused about how you took away the n like exponential or on top the blue lettering. Like I was confused about that stuff a little bit.
Like how I got the blue from this?
Yeah.
Okay, so n plus 1 factorial by definition is n plus 1 times n minus 1 times n minus 2 times n minus 3.
Oh, okay.
Right? Keeps going.
Yeah.
But if you look at this piece, all of that, that's n factorial. And so in front, you would have an n plus 1. So it's just take this one, and then all these factors together is what n factorial is.
Okay.
Understand?
Yeah, now I understand.
Okay. So the big thing that you need to know is this: n plus 1 factorial is equal to n plus 1 times n factorial. That's the big thing you need to know.
Okay.
Now, what about this? You have to be super careful here, because I'm thinking you might want to say, oh, look, on the inside, I get infinity over infinity, and I'll do L'Hopital, and I'll get 1 to the n, right? And 1 to any power is 1. That's wrong. That is not correct. So go back and look at the last problem. Didn't I just do that, though? Didn't I tell you, hey, look at the green part, and that turns out to 1? And then I said 1 to the 4th is 1. That's true. 1 to the 4th power is 1. This thing in here, what's happening is it's getting close to 1, right? It's going to 1, right? It's getting closer and closer to 1, and then I'm raising it to a finite power of 4. So give me a number that's really close to 1, raise it to the 4th power, that's going to be really close to 1 to the 4th, which should be close to 1. Here's the difference. In this problem, what are we raising it to?
N.
N, and that's going to infinity, and that's a problem. That's not the same thing. So what we have to do in order to resolve this, and this is going to be tricky, watch. Limit n goes to infinity. I'm gonna take this fraction, I'm gonna write it as this, 1 plus 1 over n to the n. So what I did was just split this into two fractions, n over n plus 1 over n. There. Now, does anybody recognize this limit? This is a very special limit.
That's E, right?
That is E. That is the definition of E. So I know from my Cal 1 class students who have me for Cal 1, we did show this in Cal 1 that this is equal to E, this limit. By the way, we don't need the absolute value because everything here is positive. Okay, so I'm just going to put a gray box around this, okay, because it's special. You need to know that that is E. And E is about 2.718, right? It's about 2.718. That number is bigger than 1. Therefore, we have divergence. The original series diverges. The ratio test gave us a number that was bigger than 1, which means the original series diverges. If the ratio test gives us a number that's less than 1, we'll have convergence. If the ratio test gives us 1, we're screwed. All right, test fails. All right, last one of the ratio tests. We're gonna get a lot of practice with ratio test, all right? All right, does this converge or diverge? So what we need to first see is that this first needs to be converted into a series. All right, we need to somehow rewrite this as sum n equals 1 to infinity, or we can start anywhere we want, but I'm gonna try and start it at 1. All right. Now, I don't recall in my notes for last time, did I cover something like this? I don't remember if I did. Have we seen a series like this? I think we have, but maybe not. No, this was convergence test. Yeah, I don't think we have. This is a very weird series. So let's look at what's happening. You first start off by taking, let's just look at the numerators. The numerator is 2 on the first term, and the second term is 2 times 6. The next is 2 times 6 times 10. Then 2 times 6 times 10 times 14. What would the next one be? If we had the next one, 2 times 6 times 10 times 14 times what?
18.
What is that?
18.
18, right? So it's increasing by 4 each time, right? And on the bottom, it would be 5 times 8 times 11 times 14 times, and those are going up by what each time?
3.
3. So the next one should be 17, right? That should be your next one. So how do we write that? That's a really strange series. We haven't really looked at one of these before. So let me show you how we write it. It's very odd. Here's what I'm going to do. I'm going to say that this top is going to be 2 times 6 times 10 times ... And then I want to stop. I want to stop where? So think about this. This is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4, this is a sub 5. So when I plug in 1, right, I want to stop at 2. When I plug in 2, I want to stop at 2 times 6. 3, I want to stop at 2 times 6 times 10. So these each jump up by 4. So I'm going to have to put 4n here because it jumps by 4 on the top each time. And then I want it to actually start at 2, then it's going to go to 6, then 10, then 14. So watch, let me just put this like this. 4n minus 2. Now, look, first time seeing this, just let me write it and then let's think about it, okay? On the bottom, I'm gonna do 5 times 8 times 11 times ... And I wanna jump here by 3s each time. So I need a 3n, but I wanna start at 5. So I need to add 2 to that to start at 5. So think about it. If I tell you right now that what you're going to do is you're going to add these up and you're going to follow this pattern 2 times 6 times 10, and you're going to stop when you get to here, then let's start by plugging 1 in. So if I plug in 1, where's the top going to stop? If I plug in 1 for n, where's the top going to stop?
A 2?
A 2, right? So all I get is a 2 on top. And on the bottom, if I plug in 1, I'm going to go 3 times 1, that's 3 plus 2 is 5. So I'm going to do this pattern, but I'm going to stop at 5. So I'm only going to go to the first one. Then plus, now I plug in 2 for n. If I plug in 2, then I'm going to go 2 times 4 is 8, take away 2, that's 6. So I'm going to follow this pattern, but stop at 6. And if I plug in 2 to the bottom, I get 6 plus 2, that's 8. So I'm going to follow this pattern, but stop at 8. And then I plug in 3. So if I plug in 3 up here, I get 12, take away 2, it's 10. So I'm going to follow this pattern until I get to 10. And on the bottom, plug in 3, we get 9 plus 2 is 11. So I follow that pattern until I get to 11. Do y'all see how this works? It's weird notation, but it's important that you're able to take this and convert it into this. You understand? All right. Does that converge or diverge? Well, let's bring in the ratio test. So I'm going to take the limit as n goes to infinity. Oh, okay. Here's our a sub n. This is the formula right here. That's a sub n. So first thing I need to do is take this and replace all my n's with n plus 1s. Watch. 2 times 6 times 10 times ... times 4 times n plus 1 minus 2 over 5 times 8 times 11 times ... times 3 times n plus 1 plus 2. That's a sub n plus 1. And then all over a sub n, 2 times 6 times 10 times ... 4n minus 2 over 5 times 8 times 11 times ... 3n plus 2. Absolute value. Whoa, that is crazy looking, right? But this equals, let's see, limit n goes to infinity. Right, I'm going to flip the second one up. Okay, I'm going to flip the second one up, but I'm also going to, I'm actually going to distribute my 4 through and my 3 through right there. Okay, so when I do that, I get 2 times 6 times 10 times ... I get 4n plus 2. I distributed 4 through, I got 4n plus 4, and then take away 2. Over, and then this one down here is 5 times 8 times 11 times ... And then here I should get 3n, distribute the 3 through, 3n plus 3 plus 2, so plus 5. That's the numerator. Now I'm multiplying by the reciprocal of the denominator. So I get 5 times 8 times 11 times ... 3n plus 2. And then 2 times 6 times 10 times ... 4n minus 2. Oh, that's where we are. Questions here? All right, now I get to cheat a little bit here because I can copy and paste. I'm going to take this answer. Watch what I'm doing. See if it'll let me do this. That actually worked out pretty good. All right, this is the same problem, right? I just rewrote it, but I put a space in here. The reason I put a space in here is because I want you to think about what would be the factor right in front of this one. So remember, each of these you said in the numerator, each of them jump by how much? These numbers, 2, 6, 10, they each jump by 4, right? So if you do the one that's in front of this one, wouldn't it be 4 less than this? What's 4 less than this? Take 4 away from this, and what would you get?
4 minus 2.
4n minus 2. Okay, and then on the bottom, the pattern was it jumped by 3 each time, right? So if I take this one and I tell you to go the one right before it, you do 3 less, right? And 3 less than that is what? 3n plus 2, right? Do you see why I did that? It's going to help me see all this canceling. This 2 cancels with that 2, this 6 with that 6, this 10 with that 10. All these dot, dot, dots cancel with all these dot, dot, dots, and I get to the 4n minus 2, and I cancel that 4n minus 2. That's where I have to stop. And then the 5 and the 5, the 8 and the 8, the 11 and the 11, all the dot, dot, dots cancel. And then the 3n plus 2, 3n plus 2. And that means the only thing left here is this. And so now I'm taking the limit as n goes to infinity of the, I don't need the absolute value, but I'll put it absolute value of 4n plus 2 over 3n plus 5. And there's infinity over infinity. You do L'Hopital's rule one time and you get 4/3. What's the conclusion?
Diverges.
Series diverges, right? The series diverges because this is bigger than 1, right? 4/3 is bigger than 1. Therefore, the original series, right, diverges. That's a tricky one. It's tricky because this whole creating the formula. All right. All right, so that's this. Let's see. So we did the examples. We did these examples. You'll have plenty of practice with that in your homework. The last test, and this is it. We are going to be done with our tests. All right. We now have, you know, this was done. We now have the almighty ratio test. All right. And the only thing left now, we did this one today. Alternating series was already done. So all we have left is the root test. All right, that's it. And I'm not calling it the almighty root test because it really, this last test it's useful, but not used very much. Okay. We just need to know that it's there because sometimes if the limit looks just right, or if the series looks just right, then we need to know, oh, let's use that test. So what's cool about this test is that it's almost like the ratio test in the sense that you still are looking to calculate a limit and you're looking at the answer and you're seeing if it's less than 1 or bigger than 1. Okay, so you're still doing that same thing. Less than 1 gives you convergence, bigger than 1 gets you divergence, equal 1 gives you nothing. It's just the thing you're doing the limit of is different. Instead of doing that ratio, you're doing the nth root of the absolute value of the sequence within the series. So let me just show you this with examples because it's easiest explained with examples. Where is it? Oh, I'm in the wrong section here. Well, I'm way off. There we go, with the root test. Here we go. So look at this series here, all right? Let's see if this converges or diverges. Well, right off the bat, I see that there's an nth power on the whole thing, right? There's an nth power. So as soon as I see that nth power, I think to myself, root test. And so what I'm going to do is take the limit as n goes to infinity of the nth root of the absolute value of this thing. Now, do y'all all agree that everything here, the a sub n, this is our a sub n, do y'all agree that that's positive to begin with? Because everything in here is positive, and raising it to a positive power, this should be positive, right? So I don't need to take the absolute value. I can just put in here 3n plus 1 over 4n plus 3 all to the n. And do you see why the nth root test works nice here? You're taking the nth root of something to the nth power. And so the nth root and the nth power cancel each other out. And so all you're left with is the limit as n goes to infinity of 3n plus 1 over 4n plus 3. And that limit with L'Hopital one time gives you 3/4. That's less than 1. Therefore, you get convergence. Right, that converges. It's a pretty nice test whenever you have like the whole thing raised to the nth power. We'll look at this next example. This is our last example, actually. This one. It's this whole thing raised to the n squared. Okay, so in order to use the root test, what we need to realize here is that this is actually the same as 1 plus 1 over n to the n to the n. That's what n squared here means, right? N squared means you're multiplying n times n. And so if I wrote this 1 plus 1 over n to the n and then raise that whole thing to the n, you're going to multiply these two powers together, and that gives you n squared, right? So that's just another way of writing the same thing. And now if I do the root test, I take the limit as n goes to infinity of the nth root of that expression. And so the nth root kills off the outside n power. It doesn't kill off this one, just kills off that outside one. And that leaves us with this limit. And we should recognize that because we just did that a second ago, right? That's e, which is bigger than 1. Therefore, we have divergence. That series diverges. So that's the root test, all right? Are there any questions? No? All right, well, if there aren't any questions, then here's what I'd like for you to do. I'm gonna give you a problem to work out. Yeah, let's see if you can figure this one out. So let me copy this first. Okay, here's what I want you to do. Don't write this down yet. Okay, here's the one I want you to do. I want you to look at this series, sum n equals 1 to infinity of -1 to the n over 2 to the 2n times n factorial squared. Okay. Sure. There is a series for you. Do y'all agree that that's a series? All right. You know what? I think this should start. Yeah, it doesn't matter. Yeah. Okay, there you go. I'd like to know if that converges or diverges. Okay, to save you the time, run the ratio test on that. I want to see how you do it. See how far you can get with it. This is an interesting problem. I'm gonna start working out, but I'm gonna pause my screen sharing so you can't see me working it out. You just continue. So I just launched a poll. If you're finished, just click A. If you're not finished, don't click anything. I just want to know if anyone has it yet. Does anyone have any questions? Anyone get hung up on some of the algebra here? Want me to clarify something before I go through it? I only have 3 students that say they're done, so I'm waiting a little bit longer. How about if you're stuck, click B. We go 1 more minute. Okay, I think that's been about 3.5 minutes, so let's talk about this. All right. All right, very first step, I'm going to run the ratio test. So I set up the limit absolute value. I'm going to set up the ratio. So I go into my original sequence and I replace all my n's with n+1s. So I replace the n+1 there, that 2 times n+1, and then n+1 inside there. Notice that the 2 has to distribute to the n+1 up here because it's 2 times n. So I have to have parentheses around that n+1, and then this n factorial becomes n+1 factorial, and then the whole thing's going to be square. That's the plugging in of n+1. And then I divide it by the original sequence with just the n's the way it appears in the actual series. Any questions on that first step? We're good? Okay, now the thing is, what do you do, right? So the next thing that I did was I said, okay, anything with the -1s, that all goes away. All right, that's all gone. And then what I did was I flipped the second one up, okay? And then watch what I did here. I'm going to distribute this 2 through this parentheses, 2 times n plus 2. So that's this step. Let me move it up so you can see it. Okay, so I took my bottom fraction, when I canceled up top, that became a 1 up there, canceled over here, this became a 1. So I have a 1 over, I distributed the 2 through, and then look what I did here. On this n plus 1 factorial, I split it into n plus 1 times n factorial, all still in parentheses squared. Because you're squaring everything in here, right? Everything in there is getting squared. So if I split that n plus 1 factorial into 2 pieces, I still have to square the whole thing. Then I take the bottom fraction, flip it, and put it here. Someone want to tell me what my next step was after this?
And factorial, you could square each of them separately and then cancel the factorial squares out.
Yeah, you can take this and split it into n plus 1 squared and then n factorial squared, because there's multiplication between those, so you can square each one. And then also, what can you do here? Turn that into 2 to the 2n times what?
2 times 2.
2 to the 2, right? 2 to the 2. That's what I did on the next step, right here. And then once you're here, well, things are real nice, because then this 2 to the 2n cancels with that. The n factorial squared cancels with that. And that's pretty much it. I mean, all you're left with here is 2 squared, that's 4. So we have 1 on top, we have 4 on the bottom. We still have the n plus 1 squared, but everything else has gone away. And that limit goes to 0, because you have a fixed number on top and infinity on the bottom, and that's definitely less than 1. And so you get convergence. Okay. That problem was just to show you how these things work out, right? When you have n plus 1s in weird places. All right. I'm going to give you all a bonus question, not a bonus, a homework problem for you all to do, separate from your regular homework. I'm going to give you a different kind of a challenge problem in a second. Are there any questions over this, though? Anything that we went over here today? Because we're done. We're done with this section 8.4. Do your homework for this section. All right. All right. So I'm going to just start off. We only have a few minutes, but I'm going to just get you going here on the next section, power series. So we're supposed to spend 2 days on this, and we were supposed to start it today. Obviously, we're a little bit behind. So let's just talk about where we are. I do not believe that I've posted these notes yet. What the heck? Why'd that go away? All right, so where we are. Okay, we have now established all the tests that we have to determine whether or not a series converges or diverges. We've got them all now. All right, all the tests. We've been through them. You've got homework assignment. We're now going to define a new type of series called a power series, right? And I want you to pay close attention to the definition of a power series, because it's going to have something in it that has not been there the whole time we've been doing series. It's what makes a series different than a power series. They're two different things. So here it is. A power series is a series of this form. Sum n equals 0. We always start power series out at 0 to infinity of c sub n times x to the n. So what we've been doing, right, up to this point, we've been doing our general version of a series has always looked like this. We first started with n being 1, and then the general idea is that we have something here, some formula, right, which was actually our sequence, right? And we're just adding up all those pieces of the sequence. But every time we plugged an n in, right, when we plugged n into this formula, let me just give you an example underneath this. Let's say we had n over 4 to the n, something like that. We would plug in 1, we would get, let's say, 1/4 here, then plug in 2, we would get 2 over 4 squared, and then plug in 3, we would get 3 over 4 cubed. But every time we did this, this was a number, right? Number, right? Each time. And so we're adding up a bunch of numbers. What's different now is that we now have this new piece, this C sub n, okay? The C sub n that's right here, hold on. Okay, this C sub n right here is just like the A sub n used to be. It's just a formula that creates numbers. But then next to it, we have x, which is a variable raised to the power n. So if we start plugging in values of n, starting at 0, we'll get C sub 0, and then times x to the 0 power, which is just 1. So that we just get C sub 0. That is a number. Plus, now we plug in 1. C sub 1 times x to the 1 is just C sub 1x. This right here is a number times x. And then plus then another number times x squared. Then plus some other number times x cubed. Plus ... forever. All right? So the big difference here is that instead of having just number plus number plus number plus number, we have number times x plus number times x squared plus number times x cubed plus number times x to the 4th, and you go forever. All right? That is called a power series because essentially you have all these different powers of x, right? You have x to the 1st power, x to the 0, right? X to the 1st, x squared, x cubed. These are powers of x in a series with a bunch of numbers in them. So the C sub n are coefficients, right? Well, it says it right here, coefficients of the series. So the C sub n is some formula that you have for coefficients of the series, and then x is a variable. So what's different, right? What's different, obviously, is in a power series, right? In a power series, we do not know the value of the variable x. That's what makes a variable a variable. We don't know its value, right? Which means the convergence or divergence of the series will depend on x, right? Like if I give you a power series and ask you, does it converge or diverge? Well, since you don't know what x is, you won't be able to tell me. The only way you'll be able to tell me is if I say, okay, does this power series converge? And I give you a value of x. So if I say like, hey, if x is 2, does it converge? If x is 1, does it converge? If x is 5, does it converge? I would have to ask you to plug in different values of x. Does that make sense? So because the convergence or divergence of the power series depends on the value of x, we can actually look at a power series as a function. A function. Think about, I mean, we're talking about functions like, go back to like when you first learned functions. If I give you something like x squared plus x plus 1, right? Yeah, let's do that over x. Okay, that's a function, right? I could ask you to plug in values of that. If I asked you to plug in 1 into this, you could give me an answer, right? If I tell you to plug in 2, you give me an answer. If I tell you to plug in 0, what would you tell me? If I ask you to plug 0 into this, what would you tell me?
Undefined.
It's undefined, right? You would tell me you can't plug in 0 because 0 is not in the domain, right? That's what you would tell me. So I can't plug in 0. 0 is not in the domain of this function. You can plug in everything but 0. Do you agree? So like if you look at this function as taking values in, right, and sending them through the function, your input and your output, you can plug any number in just as long as the x you plug in isn't 0, then it's going to get sent somewhere, isn't it? As long as it's not 0. 0 is not in the domain. So this function that we are now trying to define a function, all right, we are going to define a function as follows. It is some power series. The convergence of that power series will depend on the x I plug in. We just said that. Convergence or divergence of that will be completely dependent upon x. Therefore, this function has as its domain all the values of x such that that series actually converges. This is strange. What we're looking for is if I define if I define a function to be a power series, your task is to tell me the domain of that function. You have to go figure out what values of X make it converge or diverge. So I'm out of time. We'll get into this. We're going to get into the examples and stuff and actually generalize it a little more. And this will get kind of messy, but I wanted to at least get you to start thinking about the difference between a regular series and a power series, that we have this new variable X. And because we have a variable X, we can look at it as a function. Let me see here. Let me get that problem for you real quick that I want you all to do. Give me just a moment. Do you all have any questions while I'm looking this up? How are y'all feeling about things?
I need to study more.
What's that?
I need to study more, that's for sure.
Yeah, there's a lot of work ahead of you still. I know we're getting to the end here. This is the part of Cal 2 that gets really hard because you're right here at the end. It feels like the end, but the last 3 or 4 sections are just, there's a lot of material. So all of chapter 8. Let's see, here we go. Let me grab the sucker for you. I know you can't see it yet, but oh, you know what? I'm in the wrong section. Almost there. Thank you for your patience. I'm just writing it down real quick. Sum n equals 0. I know you can't see this yet. Okay, there you go. So there's a series, all right? There is a series, and I want you to run the ratio test on this and tell me if it converges or diverges. After you do that, I want you to consider something, all right? I want you to imagine that you took this, right? Take this. I made 3 copies of it, and I want to ask you this question. If I were to plug a number in, like up top, if I were to put, like, let's say the number 5 here, or if I put the number -4 here, or if I put the number 10 here, would that change your answer at all? Okay, so first do this, do your ratio test. Tell me what happens, convergence or divergence. And then look at what happens if you were to add a constant out here. Would that change the answer or not? Would you still have convergence or divergence? Would it change? Okay. Make sure you do all your homework. You should be good with all your homework through 8.4 by the next time we meet. And we're going to hit 8.5 hard. Hopefully we'll finish it next class. All right, everyone. I'll hang out for a little bit if you have any questions. Otherwise, have a good day.
Excuse me, sir.
Yes, sir.
Can we talk about my test?
Yes, we can.
Yeah.
Trying to figure out who else is in here because I don't know who one of
Yeah, I
them.
don't know. Oh, they
Okay,
left.
they're gone. Okay. Let me do this. Let me just lock the meeting real quick. There we go. Okay, let me pause my screen real quick so I can get to it without showing you other people's tests. Yeah, so you understood my concern, right? I was just
Yeah.
concerned about the way you did it, whether or not you, had done this. It just looked like it was just like kind of copy pasted out of.
Oh, no. Can I